From breathtaking mountainous terrain to extravagant underground cavities, these rock formations are a testament to Earth's extensive history and time. Water and gravity carved these ancient rocks into stunning forms that fully demonstrate nature's innate beauty and power of creation. In the 19th century, the term Karst was adapted from the German language to describe all landscapes that share these qualities. Karst topography is characterized by jagged, mountainous landscapes, sinkholes, and ground caves. These unique features are the result of water chemically interacting with the carbonate rock landscape. Karst topography covers 15% of Earth's land surface. China has the highest area of exposed carbonate rocks globally at an estimated 1,300,000 square kilometers, about 14% of the country's territorial area. The South China Karst Center at Guizhou is especially spectacular because adequate rainfall in the region allows topographical traits to develop fully. The outstanding aesthetic and scientific qualities of the South China Karst led UNESCO to declare parts of it as World Heritage Properties in 2007 and 2014 for preservation. Carbonate rocks are responsible for providing karst topographies with their unique aesthetics. Limestone, a rock composed of calcium carbonate, is a sedimentary rock most associated with karst topographies. It formed millions of years ago below the ocean surface by deposits of diseased ancient aquatic organisms. In this process, limestone acquired its layered appearance and chemical composition. As the Earth's crust shifted, shorelines retreated, and limestone landscapes emerged from the water. For the next millions of years, rainwater eroded away parts of the rock, leaving behind spectacular formations. Compared to igneous rocks, limestone can be relatively easily eroded by slightly acidic water. Under natural circumstances, water can combine with carbon dioxide from the atmosphere or the soil to form carbonic acid. This slightly acidic acid composition is effective at dissolving limestone. The calcium carbonate in limestone reacts with carbonic acid to become an aqueous solution. Rainwater can seep through cracks in the limestone, enlarging them over time. This development leads to various iconic features of karst topography. Glancing at the horizon, one might recognize the silhouette of a bridge spanning across two mountain peaks. However, this bridge is not of anthropogenic origin. Instead, it is a natural bridge. Natural bridges occur when low-tide water travel underneath hills, eroding to their bodies while preserving a stone arch above the erosion valley. At Guizhou River Scenic Spot, this phenomenon is critical to a unique scenery that occurs exclusively in the morning. When sunlight shines through the opening in the mountain, a beam of light is casted upon the river flowing underneath. While a stream is visible in this example, it is essential to note that in many cases, the water systems responsible for the bridge's creations may have disappeared long ago. Blind valleys are developments similarly affected by water flow. They are defined by valleys that appear to have an abrupt end, where streams approach cliffs. This counterintuitive formation is possible in terrain where a porous rock layer, such as limestone, is positioned above an impermeable one. The formation process commences when streams of water travel inside the porous layer beneath the surface, eroding it until the surface collapses. Water continues to erode the terrain, eventually creating a flat-bottomed valley. However, unlike traditional valleys, streams in blind valleys have no visible outlet. Instead, they tend to escape through sinkholes and are redirected underground. For this reason, the ends of blind valleys are usually steep and dry. Following the streams underground, one will be greeted by massive cavern systems. The high water velocities make these incredibly complex systems challenging to explore. Refined into shape by underground water channels, karst caverns create unique sceneries within. A cave's formation initiates when water seeps through limestone cracks and erodes them. As water continues to erode the surrounding walls, the channel widens and has increased water volume. Eventually, these erosions lead to large underground cavities. Droplets of rainwater carrying calcium permeate through the limestone layers. As water droplets fall, they deposit calcium carbonate on the ceiling, forming stalactites. Stalagmites, referring to stone cones forming on the floor, are created in a similar process. On some occasions, stalactites and stalagmites can connect and form columns. This process occurs over tens of thousands of years. The Jianjing caverns are among the most renowned cavern systems in the world because of the exemplary features of Karst influence. One of the most prominent pieces within the cavern is a stalagmite resembling a general's battle helmet. The unique qualities of this stalagmite were only possible under specific circumstances, where the chemical composition of water and the ambient temperatures allowed the development of one type of stalagmite over another. 150,000 years ago, a relative abundance of water droplets formed a cap-like stalagmite on the cavern floor. As time progressed, water droplets became less abundant. Therefore, stem-like stalagmite grew on top of the pre-existing structure, contributing to the unique scenery. Correlated with these fascinating underground formations are sinkholes. Sinkholes are surface depressions formed when underground cavities collapse. There are generally two situations that can lead to the formation of sinkholes. In science, soil is categorized by its makeup of sand, silt, and clay. Sand refers to the largest particles in the soil, usually 2 to 500 millimeters in diameter. Clay defines the smallest particles in the soil, less than 2,000 millimeters in diameter. Silt is the rest of the particles that lie in between the two. In areas where soil is mostly sand, erosion may create cavities in the carbonate bedrock, leading to a surface depression forming gradually as sand drains to fill in the cavities. Distinctly, in areas where soil is mostly clay, underground cavities may remain invisible on the surface until they completely collapse, forming sinkholes in an instant. Sinkholes come in various shapes and sizes. The largest sinkhole is in Chongqing, China, at a record-holding depth of 662 meters. In the context of time, water can mold and shape objects as immovable as stone. As the Karst hydrological system approaches an end, water emerges from the rock layers as springs. Karst springs usually share a high discharge rate as they converge rainfall upon entire erosion basins. However, their flow are often seasonal as they are heavily dependent on rainfall. Some springs, in this fashion, remain dry for most occasions of the year. Much of China's southern region is characterized by karst formations. As they become increasingly interconnected through highway systems, bridges have become necessary to facilitate travel within the mountainous terrains. Not only do the valleys and mountains pose significant obstacles, but the easily eroded carbonate rocks also present distinctive complications for bridge building. As of the fourth quarter of 2022, the Ministry of Transport of the People's Republic of China estimates upwards of 28,000 motorway bridges in Guizhou, nearly 80-fold increase since 1949, when the number was only 357. The unique geological features of karst terrain have led to countless innovations in advancing bridge construction technology worldwide. Nearly half of the 100 highest bridges in the world are located in Guizhou. The incentivization of universalizing bridges continue to drive the growing interconnectedness of Guizhou and the regions adjacent to it. Construction of bridges in karst landscapes is a complex process that requires thorough understanding of the rock foundations at the planned site. Scientists survey the topographical characteristics of the construction site beforehand with ground-penetrating radars, electrical resistivity tomography, and other computing methods. Creating a bridge must strike a perfect balance between cost, quality, project duration, and design. Guizhou is home to all types of bridge designs. The Huayudong Bridge was the first arch bridge built in Guizhou. Its unique design qualities factored in aesthetics and allowed it to minimize disturbance to local lake ecosystems, which also serves as a drinking water source. The bridge was initially constructed in 1991 and experienced a full reconstruction completed in 2021. In 2022, the remodeled bridge was awarded the Gustav Lindefeld Medal, one of the most prestigious achievements of bridge engineering awarded by the International Bridge Conference for outstanding innovation and environmental harmony considerations. In close approximation to this bridge is the Huayudong Hou Bridge. When the bridge became operational in 2004, it was the province's first case of an asymmetrical, single-towered, pre-stressed concrete bridge. The bridge was designed for two-directional high-speed traffic with 4 lanes. In 2019, the Pingtang Bridge, spanning 2,135 meters, was debuted. The cable-stayed bridge took 3 years to complete as an essential project of the Yuqing to Anrong Expressway. The bridge was nicknamed the Bridge of the Sky, derived from its incredible height. Moving further south, we arrive at the iconic Baling River Bridge. As a suspension bridge built directly on top of the erosion-prone Karst Valley, the Baling River Bridge required complex engineering solutions to ensure its safety of operation and lifespan. Suspension bridges work primarily by utilizing the tension in cables to support the bridge's weight. The cable then transfers this tension into the terrain on the 2 ends of the bridge. Two commonly used techniques for fixing the cables are gravity-type anchorage and tunnel-type anchorage. Gravity-type anchorage uses vast masses of concrete to pin down the main cables. This solution requires large quantities of concrete and is considerably destructive to the environment. However, it has a lower requirement on the construction site's rock properties. Experts consider tunnel-type anchorage, on the other hand, a superior solution regarding project scale and protection of nearby ecosystems. There are wedge-shaped tunnels that relieve tension in the cables into the surrounding terrain. Tunnel anchorages are primarily composed of 5 components. The main cables transfer tension from the bridge into the anchorage. The splay saddle is a concrete component that fixes the cable and allows it to angle flexibly. The cable is split into various single strands beyond the splay saddle. Traveling further into the tunnel, the plug body transfers the tension force in the cables into the walls. The plug body divides the tunnel into 2 sections. The chamber above the plug is the front room, whereas the chamber below it is the rear room. Baling River Bridge adopted gravity-type anchorage on the east bank and a tunnel-type anchorage on the west bank. The main engineering challenge of the tunnel-type anchorage is to resolve erosion issues on the contact surface of the anchor body and the terrain. The rock formations on the west bank of Baling River Bridge are composed primarily of limestone and dolostone. Both are carbonate rocks prone to erosion. The construction of the tunnel-type anchorage altered the local underground water flow. Because concrete is impermeable, water must circumvent the anchor body while flowing through the rock layers. This causes erosion of the surface where concrete contacts the rocks. Erosion can weaken the bond between the two, reducing their frictional force. This will shorten the bridge's lifespan. To resolve this issue, engineers enhance the side slope surface to redirect water away from the structure. Karst formations have repeatedly shown their ability to create wonders using only 2 key elements, water and time. Guizhou's unique karst influence is nature's most significant legacy, including scenic rock formations and breathtaking bridge architecture. It continues to serve as a reminder that even the immovable rock can be redefined by patience and time. Its influence on bridge architecture will perpetually drive new generations of innovation worldwide.